Hi everybody, welcome to Chemistry Week 4. I'm recording this on Friday, the week before Week 4. And you guys will be watching this, hopefully, in about 5 days' time. So I'll be away this week, and I'll do this in 2 parts because it's quite intricate. So we'll do chemical bonds and Lewis dot structures, and then I'll do another maybe 20-minute separate video on molecular geometry, and I'll upload them together as part 1 and part 2 of week 4. So we're going to talk about chemical bonds, so the bonds between 2 atoms that make up a compound. We have ionic, metallic, covalent bonds, and covalent bonds are split into polar and non-polar covalent bonds. So covalent bonding is between non-metal atoms. And I'm just going to go straight into the whiteboard because why not? So you can see, just follow along on the slides because I've sent them all to you. Okay. 11-12 biology seminar. So covalent bonds. Now we have, again, this is hopefully just some revision for you guys. We have group 1, 2, 3, 4, 5, 6, 7, 8. We know that group 8 is the noble gases. And all of these atoms want to react with each other, react with something to attain the state of the noble gases. And that is to have a full outer shell or outer electron shell. And for most of them, that is 8 valence electrons. Group 7 has 7 valence electrons. Group 6 has 6. Group 5 has 5. Group 4 has 4. 3 has 3. Group 2 has 2. And group 1 has 1. And what they do is they share these outer electrons to achieve this state. So hydrogen, again, simple example. Okay, actually it's probably not the best example because it breaks the rule. Hydrogen only needs 2 electrons to achieve a noble gas configuration. Whereas the rest need 8. So hydrogen, 2 hydrogen atoms come together, and if we think about the outer shell, or the 1s shell, then they share the outer electron that they have, the one that they have. So then they both have 2. Happy days. They're in their stable, noble gas configuration. So it's just basically a shared pair of electrons, and we'll go through that when we look at Lewis dot structures. And this small group of covalently bonded atoms we call a molecule. So chlorine has 7, it's a halogen, so it has 7 valence electrons. So if we put them around like this, and then they share this pair in the middle. This is the bonding pair in a covalent bond. Bonding pair here, they're sharing these 2. And they both have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They're both happy. They're sharing the electrons. And we'll go through building these. These are what's called a Lewis dot structure in this seminar. So in drawing Lewis dot structures, we have to, so the first step is we sum the valence electrons. Sum the valence electrons. So the number of valence electrons is the group number. Simple. So write atomic symbols for the atoms. So chlorine, to show which atoms are connected to which. So we have the most electronegative atom in the middle. Least electronegative. In the middle. Then we connect, put 1 dot as a bonding pair. And then we make everything else into an octet state. And I'll show you how we do this with an example. Trying to explain it without an example is a bit silly. So NH3 trying to draw a Lewis dot structure. So I want you to do this along with me if you've got a pen and paper, so I'll take my time. So the first thing we do is find how many valence electrons. So nitrogen, where is nitrogen? So where's nitrogen and where is hydrogen? Hydrogen is group 1, and there's 3, so we times it by 3. So nitrogen is in group 5, so 5. There's 8 valence electrons. So now we go back to our steps. So we've got 8 valence electrons. H3. Eight, I just call them VE valence electrons. So if there's 1 of nitrogen and 3 of hydrogen, then nitrogen is going to go in the middle. So define. So nitrogen will be. So we then put our bonding pairs in. So that's 1, 2, 3, 4, 5, 6. So we've still got 2 left over. So they go around here because that makes nitrogen has an octet. Hydrogen, we know, is the exception to the rule. And it only needs 2. So another example of how we do this. C2H4 or ethane. We've done the biology, organic chemistry. We'll know this one. So carbon goes in the middle. And how many hydrogen have we got? Sorry, it should be C2H6, not 4. My apologies. So we then now put in the bonding pairs. Actually, first we find out how many valence electrons. Sorry, I skipped the Q. So carbon is in group 4. So 2 times 4 equals 8. Hydrogen is in group 1. So we have 14 valence electrons that needs to be involved in this system. So we put our bonding pairs. How many is that one? That's 12. So we need to put a bond between the carbon and carbon. And now we count. So 1, 2, 3, 4, 5, 6, 7, 8. Carbon is happy. All the hydrogens are happy. These 2 carbons are sharing this pair. 2, 4, 6, 8. All the carbons are happy. There's 14 valence electrons there. Everyone's happy. So CO2. And this is where things start to get a bit weird. So find me how many valence electrons should be here. Carbon is in group 4. Oxygen is in group 6. What I want you to do is figure out which one of these should go in the middle. So carbon is the least electronegative, and oxygen go one on either side. So we've got 16 valence electrons here, but we've got 3 atoms. So we start with bonding pair. Now the molecule is bound together. And then we try to make octets around everything. So this is how we would do it. Keep in mind how many valence electrons you have to play with. So, fantastic. Everything has an octet now. Doesn't work, does it? 6, 14, 20. We don't have enough electrons. Now, this is where the concept of double bonds comes into play. So we know that the 2 carbons can share, carbon and the oxygen and the carbon and the oxygen can share 1 pair of bonding electrons. With oxygen, you typically get, they share a double bond. So they're sharing 2 pairs of electrons. So there's now 4 electrons on all of these. So if we want to make everything to an octet, this is a double bond. So we'll call it a double bond in covalent bonding. We can then make octets, 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. Tick. Oxygen is on here is good. Carbon here, 1, 2, 3, 4, 5, 6, 7, 8. He's happy. He's got this octet. One, 2, 3, 4, 5, 6, 7, 8. So, and we check 2, 4, 6, 8, 10, 12, 14, 16 valence electrons, and we know we've done it right. I'll record a second part to this, well, straight after this, and upload it. Well, we actually learn what shape things are based on this. So H2O. I'm going to give you 30 seconds to figure out how many valence electrons it has. So what group is hydrogen in? Group 1. Oxygen. It's got 8 valence electrons to play with. This is where we're going to get a bit. So, So oxygen goes at the top, hydrogen down here. So we put our bonds. We can also, for ease, have just draw a line and you'll get the same, indicates the same thing, a pair of electrons bonding. Now, I'm probably going to jump ahead here for a second. We're going to talk about something called hydrogen bonding. And oxygen is over here in group 6 on the far right. Hydrogen is over here. The electronegativity value of oxygen is really high. The electronegativity value of hydrogen is not so high. So what happens here is oxygen hogs the 2 electrons from hydrogen. So we have, how many electrons do we have? So we have 8 valence electrons. One, two, three, 4 bonding pairs, which gives us 8 valence electrons. I'll jump ahead a little bit. So oxygen in water is actually O2-, and the hydrogens are positively charged. Now, remember that as we work through now into hydrogen bonding. We'll go into metallic bonds first. So metallic around all of these metal ions, you have this sea of free electrons. They're negatively charged, the metals are positively charged. And in that, all of these electrons keep everything bound together. I wouldn't worry too much about it, it's just mostly for interest's sake, because you're not really going to look at it in high school. So the negatively charged electrons keep the metal ions together and happily bound together. So the outer electrons separate from their atoms and become delocalized, and you get this sea of electrons. The atoms become positive ions and they're attracted to the electrons. So these positive metal ions should repel each other, but they don't because of the sea of negatively charged electrons. Again, you're not really going to come across that a huge amount. So because of this sea of electrons, it conducts heat and electricity, and the bonding is very, very strong. So the melting and boiling points of metals are massive. And they can easily shake them because they have this sort of sea, almost like a liquid sea of electron. Electricity will just follow the sea and come out the other side, as will heat. So the ionic bond we talked about between a metal and a non-metal, NaCl. Sodium chloride. Na is in group 1, So chlorine is in group 7. Chlorine, sodium gives its 1 electron to chlorine. Chlorine now has 8 valence electrons. Sodium now has 8. Now they're happy days together. And you can tell what is going to react to make what compound based on where they sit on the periodic table, and I'll explain that in a second. The ionic bond is the electrostatic attraction between positive and negative ions. Sodium gives away its electrons, it becomes positively charged. Chlorine accepts the electron and becomes negatively charged. That electrostatic attraction between them is why ionic bonds are so strong. And they also form these lattices. I mean, you guys know my artwork isn't great. Pretty sure there's a picture on the next slide. There you go. So sodium and chlorine, they make this ionic lattice. And that is why some ionic compounds will form salts and crystals, like sodium chloride does, and others don't. So the ionic bond strength depends on ionic charge. So the higher the charge, the stronger the bond. So 3 plus with 3 minus is stronger than 1 plus and 1 minus. So the radius of the ion, so you want this charge to be spread out over as small an area as possible. If it's over that much area, then this one will be significantly stronger. So if we look at the periodic table, group 1. The groups on the left will form. So group 1 elements lose 1 electron to form +1 ions. Group 2 lose 2 electrons to form +2 ions. So magnesium and oxygen turn, and we get magnesium oxide. So group 6 elements, which is oxygen, gain 2 to form -2 ions. So ionic compounds dissolve in water. So what usually happens is NaCl will dissociate into Na and Cl- in a solution. Aqueous solution. So the high melting points and high boiling points, it's because those electrostatic forces take a lot of energy to break. Once they're in that lattice formation, the bond energy is really quite high. If you have solid sodium chloride, it's in this lattice. So this doesn't move, so it can't conduct electricity as a solid. If you put it into a solution, you have Na ions, and the electricity can pass through. but they cannot do it as a solid. Or when they're melted, they can conduct electricity because the ions are free to move. As a solid, they are not free to move. So, forces between the molecules. So, we have three. We have dispersion forces, or van der Waals, depending on where in the world you are. These are the weakest forces, and they are not between the atoms in a molecule. They are forces between the molecules. They are intermolecular, not intramolecular. So, we have a hydrogen atom, Hydrogen has one electron, but we can't determine where it's going to be at any one point. So at some point, it's going to be over this side and not have one over here. So this side is negatively charged and this side is positively charged. And any other molecules that line up like that will have this very, very weak and fleeting electrostatic attraction. So, weakest between the temporary dipoles of an atom. Temporary dipoles in an atom. Positive, negative. Eventually the electron comes back around and the bond's broke. It's really quite fleeting and not very strong at all. We then have dipole-dipole forces. I mean, not the most creative name in the world. So, we have covalent bonds, right? Learned about them, we know all about them. If the atoms in a covalent bond are a significant distance apart from left to right, then they have a significant electronegativity difference. So, if that happens, then one of the elements is going to hog the electrons, and there'll be a negatively charged side and a positively charged side. So water is an example of that. The oxygen is negatively charged, the hydrogen is positively charged. So another atom comes along, it's negatively charged on this end, positively on that end, and you get an electrostatic attraction between the two. It's stronger than dispersion or van der Waals, what do you want to call it? But they're still not that strong. Still an intermolecular force. You can read along on the slides as I'm just kind of doing my own thing, as I do. So, hydrogen bonds, very, very important for biology, very important for everything. If hydrogen bonding was ever so slightly different, we wouldn't be here. And it is when, for example, oxygen, nitrogen, or fluorine is bound to hydrogen. Hydrogen is not very electronegative, whereas these three are, and they love to bind with hydrogen, and they love to hog the electron. So we'll stick with oxygen because it's nice and easy. So oxygen, we know it hogs the electrons. So this has a 2- charge. Hydrogen has a positive charge. Along comes an oxygen with a bonding pair of electrons free, spare. Hey, look, it's their lucky day. They now have a really strong electrostatic bond with the oxygen. This only occurs when oxygen, nitrogen, or fluorine bond with hydrogen, because they are very, very electronegative, and hydrogen is not. So they will hog the electrons, and they're very important for biology. So they have the characteristics of a dipole-dipole attraction, and also characteristics of the covalent bond. So really, 2-, 2+ coming together. Happy days. It is 1/10 the strength of the covalent bond. So it's not massively strong, but it's stronger than the other two. So, yeah, so when hydrogen is covalently bound to fluorine, nitrogen, oxygen, you get hydrogen bonds occur. So water is the most classic example of hydrogen bonding. Hydrogen bonds are what makes water water. And if it was ever so slightly different, we wouldn't be here. I know I always say that. So, oxygen binds to hydrogen in a hydrogen bond, creating a very strong attraction. So I'm going to leave it there and record the rest in a little while, and I'll upload them both.